Hello everyone, my name is Dennis. In this video, we will discuss about Chapter 1, Physical Quantities and Measurements.
This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out important updates from us.
Physical quantities and SI units. A physical quantity is a unit that can be measured. It consists of magnitude and a unit. So for example, we are talking about the length. The length of a flagpole is 5.5 meters. So this length is the physical quantities. 5.5 will be the magnitude and meters m here is the unit. What is SI unit? SI unit is a standardized units that are used worldwide. There are two types of physical quantities, base quantities and derived quantities. Base quantities. Base quantities are quantities that cannot be derived from other quantities. They only can be measured. There are 7 base quantities, which is listed in this table. The first one, the length. Common symbol is L, SI unit meter, symbol for SI unit M. Time, common symbol is T, SI unit second, symbol for SI unit S. Mass, common symbol is M, SI unit kilogram, symbol for SI unit kg. Temperature, common symbol is theta or T, SI unit Kelvin, symbol for SI unit K. Electric current, common symbol is I, SI unit ampere, and symbol for SI unit is A. Amount of substance, common symbol is N, SI unit mole, symbol for SI unit is MOL. And luminous intensity, LV, SI unit candela, symbol for SI unit is CD. Derived quantities. Derived quantities are quantities that are derived from base quantities. Their corresponding units are called derived units. Basically, any other quantities not in 7 base quantities are derived quantities. So here are a few examples. Like speed, it is derived from distance divided by time. The SI unit is meter per second. Symbol for SI unit is m/s or ms to the power of -1. Then volume, for example, the volume of a cuboid is width times length times height. The SI unit is meter cube, and symbol for SI unit is meter to the power of 3. Then force is, we know that is F equals to ma. SI unit is kilogram meter per second square, or more commonly we are known as Newton. As symbol for SI unit, kilogram meters as -2 or capital N for Newton. Prefixes. So prefixes are used to express quantities that are very large or very small. So let's see how we can memorize it easily. We start with the one that we commonly use, the 10 power 3, which is the value is 1000. Prefix is kilo, symbol is small letter k. Then 10 power 6, the value is million, the prefix is mega, the symbol is capital M. 10 power 9, the value is billion, prefix is giga, symbol is capital G. Then 10 power 12, the value is trillion, prefix is tera, symbol is capital T. Okay, so this one, when we go up, the values are getting bigger and bigger. Now we move down, right? The first one is 10 power -1, which is value is 1 over 10. Prefix is deci, the symbol is small letter d. Then 10 power -2 is value, its value is 1 over 10, 100, and the prefix is centi, symbol is small letter c. And 10 power -3 is 1 over 1000. Prefix is milli, symbol is small letter m, 10 power negative 6, which is 1 over 1 million. Prefix is micro, and the symbol is mil. 10 power negative 9, which is 1 over 1 billion. Prefix is nano, and symbol is small letter n. 10 power negative 12, the value is 1 over 1 trillion. Prefix is pico, and symbol is small letter p. So when we move downwards, the value is getting smaller. Standard form. Sometimes standard form is used to represent big numbers or small numbers, especially when doing calculation. So it helps us to do calculation for very big number or very small number easily. So the format of standard form will be a times 10 power n, where a is in between 1 inclusive 1 to less than 10, and n is an integer. So for example, which of the following value is smaller, 280 micrometer or 0.0028 centimeter? So let's see how we convert into standard form and do the comparison. 280 micrometer equivalent to 280 times 10 power negative 6 meters. So this is not a standard form. We need to move the decimal place. For this case, we move the decimal place from here 1 to 2 units to the left. So the power negative 6 here, we need to plus 2 becomes negative 4. Okay. The next one, 0.0028 centimeter equivalent to centi is times 10 power negative 2 meters. And again, this is not a standard form. We need to move the decimal place here, right? 1, 2, 3. So 3 decimal place to the right. Then it becomes 2.8 times 10 power negative 3. So when you combine these two, 10 times negative 3 times 10 to the power of negative 2, right? And we get 2.8 times 10 power negative 5 meters. So when you compare these two numbers, we find that 0.0028 centimeter is smaller. Scalar quantities and vector quantities. Scalar quantities are quantities that have magnitude only, for example, time and mass. Vector quantities are quantities that have magnitude and direction. For example, velocity of a car, 50 kilometers per hour to the west, force moving a box is 10 newtons upwards. So you can see that we have 50 kilometers per hour, this is the magnitude, and to the west, this is the direction. 10 newtons, this is the magnitude, upwards is the direction. We can add or subtract directly numerical values of scalar quantities. For example, 10 kilograms plus 2 kilograms equal to 12 kilograms. 10 seconds minus 2 seconds equal to 8 seconds. When adding or subtracting vector quantities, both magnitude and direction need to be considered. We can use tip-to-tail method to do this. Tip-to-tail method. So these are the steps. First, the tip of vector arrow connect to the tail of another vector. This is vector 1, which is 10 cm, plus with this is vector 2, the length is 10 cm, but there is a certain angle here, let's say theta. When we join them together, the first vector is 10 cm, right? The tip of this vector connect with the tail of second vector. Okay, so which is 10 cm as well for this case. So the resultant vector measures from the start of the tail of the first vector to the tip of the second vector, which looks like this. Okay, so this will be the resultant vector. Let's look at another example. Let's say in a school sports game, A student runs 300 meters towards the north, then run 400 meters towards the east to the end point. What is the distance between the start point and the end point? Okay, so first we want to choose the appropriate scale. For this case, let's say I choose 1 cm to 100 meters, and let's say this is the north, right, direction of the north. So this is point A, the starting point, and the student runs 300 meters towards the north. So this is 300 meters, then stop at point B. Okay, and this length will be 3 cm. Then he runs 400 meters towards east. So this is the second vector, and it is 400 meters. So when I will measure this length as 4 cm and end at point C. This is the end point. So this will be the uh, the distance that I want to find, and I measure directly from diagram. Let's say this length will be 5 cm, and the actual distance between the start point and the end point will be 5 times 100, because we have 1 cm represents 100 meters, so it's 500 meters. Addition of two vector quantities. When two vector quantities are added together, the maximum resultant vector is obtained when the two vector quantities are in the same direction. On the other hand, the minimum resultant vector is obtained when the two vector quantities are in the opposite direction. So for example, vector 1, 3 cm, this is vector 2, 5 cm, both are in the same direction. So the resultant vector will be 3 plus 5 equals to 8 cm. On the other hand, let's say vector 1 is 3 cm, vector 2 is 5 cm, both vectors are in the opposite direction. So the resultant vector will be 3 plus negative 5. It will give you negative 2 cm. It means it is at the opposite direction. The next one, let's say 3 cm. So the first vector and the second vector 5 cm at certain angle. Both vectors are at angle to each other. The resultant vector will be between 3 cm to 8 cm. Measurement of length. The SI unit for length is meter, and the symbol is m. The common measuring instruments that we use in physics lab are meter rule, measuring tape, Vernier calipers, and micrometer screw gauge. We'll discuss more on meter rule, Vernier caliper, and micrometer screw gauge in the later part of this chapter. Each instrument is designed based on certain precision. The precision is the smallest value that an instrument can measure. This table shows different measuring instruments with its precision range and example of use. The first one, meter rule. The precision is 0.1 cm or 1 mm. The range is several cm to 1 meter. Example, the length of a book. And second, measuring tape. The precision is 0.1 cm or 1 mm. The range can be several meters, and we can use it to measure the length of the table. Vernier calipers, the precision is 0.01 cm or 0.1 mm. The range is from 1 cm to 10 cm. We can use it to measure the diameter of a pencil. Micrometer screw gauge, the precision is 0.001 cm or 0.01 mm. The range is from 0 to 1 cm. We can use it to measure the thickness of a piece of paper. So accuracy is the extent of how close a reading of a measurement is to the actual value. Reliability is the extent to which the outcomes are consistent when measurement is repeated more than once. When we do measurement, usually we'll do it a few times. The ideal case for a measurement would be the value that we get is very close to the actual value. And also, when we do a few times, the reading that we get are very close to each other. So the first picture shows the best case, where the data that we get are accurate and reliable. So when it is very close to the actual value, it will be in the bullseyes. And we'll see that each dot here represents one measurement. So they are very close to each other, then they are reliable. And all the points are at the bullseyes, then they are accurate. And we look at the second picture, right? We can see that all of the dots are very close to the bullseye, but they are actually quite further away with each other. So this data is accurate but unreliable. Go to the third picture, we can see that all the black dots are close to each other, but they are far away from the bullseye. So this data is inaccurate but reliable. Look at the fourth diagram. You can see that they are far away from the bullseye. They are also further away from each other. Hence, the data is inaccurate and unreliable. When we are conducting experiments, they might have two types of errors. The first error is systematic error, which will reduce the accuracy. For example, zero error. The second type of error is random error, which will reduce the reliability. For example, parallax error. Let's talk about parallax error. Parallax error is caused by the inaccurate positioning of the observer's eye while taking readings. To avoid parallax errors, the observer's eyes should be positioned directly above the markings. Let's look at this diagram. This is the correct positioning of the eye. The first eye is just vertically above the 1 cm marking, and the second eye is also just vertically above the 2.9 cm marking. Hence, the accurate length of the object is 2.9 minus 1.0, which is 1.9 cm. The second diagram is showing incorrect positioning of the eye. Look at the first eye, right? It is not aligned properly and will give us 0.9 cm reading. For the second eye, it will give us 3.0 cm reading. Hence, we'll get the inaccurate length of the object, which is 3.0 minus 0.9, and it gives 2.1 cm. Next, let's talk about zero error. It happens when measurement does not start from zero. Reading is shown when it should be zero. This is mainly caused by wear and tear of the instrument, because before using measuring instrument, they should be checked for zero error. If zero error exists, reading should be corrected with the following formula. Corrected reading equals measured reading minus zero error. Please remember this formula. Vernier calipers. This diagram shows the basic structure of vernier calipers. Let's look at the first part, the internal jaws and the external jaws. Internal jaws can be used to measure internal diameter or internal length of an object, while external jaws can be used to measure the external diameter or external length of an object. Then, look at the scales. For vernier calipers, it has main scale and Vernier scale. On the main scale, the top scale is inch units and the bottom is in metric units. The depth measuring blade can be used to measure the depth of an object. Lastly, the locking screw can be used to tighten the moving part of vernier calipers after we take a reading. Okay, now let's see how we can read. Now let's look at the top part, which is the main scale, right? The unit is in cm. This is the main scale, and the bottom is the vernier scale. So we'll check with the first marking, which is the 0 marking, when it appears. It appears at the 1.2 cm mark from the main scale, and we go and check which marking on vernier scale coincide with the marking at the main scale. So for this case, the third marking of the vernier scale coincide with the marking on the main scale. Hence, the reading is 1.23. Now let's talk about how to check for zero error on vernier scale, vernier calipers. First, we need to close the vernier calipers completely and look at the scale. You will get either no zero error, positive zero error, or negative zero error. For no zero error, this is how it looks like. The two zero marks coincide, and the 10th mark on the vernier scale coincide with 0.9 cm mark on the main scale. Hence, the corrected reading will be just the measured reading. So for our example, right, previously we read the scale as 1.23 cm, hence the corrected reading is 1.23 cm. If there is positive zero error, this will how it looks like. First, the zero mark on vernier scale is after zero mark on the main scale. And we check which marking on vernier scale is coincide with the marking on the main scale. So the third marking for this case. Hence, the corrected reading is measured reading minus zero error. For our case, 1.23 minus 0.03, which will give us 1.20 cm. We can also get negative zero error, which looks like this. The zero mark on the vernier scale is before the zero mark on the main scale. And we check which marking on vernier scale is coincide with the marking on the main scale. We count from the 10th mark. So 1, 2, and 3. Hence, the corrected reading is the measured reading minus zero error, which is 1.23 minus negative 0.03 for our case, and we'll get 1.26 cm. Now let's look at one more example here. The diagram below shows the main scale and vernier scale of a pair of vernier calipers used to measure the diameter of a ball bearing. Okay, so what is the diameter of the ball bearing if there is no zero error? A zero error of positive 0.04 cm and a zero error of negative 0.04 cm. First, we need to take measured reading. Check with the zero mark on the vernier scale, and it is at 5.1 cm mark. Plus with which marking on vernier scale coincide with the marking on the main scale. For this case, it is 0.04. Hence, the measured reading for this case is 5.14 cm. If there is no zero error, then the corrected reading is 5.14 cm. If there is a zero error of positive 0.04, then it will be measured reading minus zero error, which which for this case 5.14 minus 0.04, the answer is 5.10 cm. And if there's a zero error of negative 0.04 cm, the reading will be 5.14 minus negative 0.04, which is 5.18. Next, let's look at micrometer screw gauge. The diagram shows the basic structure of micrometer screw gauge. We will look at the moving parts of this instrument, which is a spindle, and the non-moving part is the anvil. The spindle will move when we turn the timber. Okay, and then we also have the sleeve here, which has the main scale in mm. The scale in the timber is in 0.01 mm divisions. Lastly, the ratchet, right, is used to make sure that the object that is being measured is being touched but not being pushed too tight by the spindle. Okay, so these are the steps to use micrometer screw gauge. Step 1, close the jaws of the micrometer and check for a zero error. Then we can place the wire or metal ball or any object that we want to measure between the anvil and the spindle end. Then we rotate the timber until it touches the wire or the metal ball. And the last step, we rotate the ratchet until a click sound is heard. Why rotate the ratchet? It's because we want to prevent the spindle from applying too much force to the wire or the metal ball. Okay, timber rotates. When timber rotates one round, 0.50 mm movement on the spindle. Okay, now let's learn how to read from the scale. Okay, we will check from the main scale in mm. So this is 2.5, this is 3.5, and this is the timber scale. We'll check which marking on the timber scale coincide with the main scale. Right? So now the next one we check here, the 4 here means this is 4.0 plus with this is 12, which is plus 12, and then at the end we'll get 4.12 mm. There's another case where we can see that firstly, of course, the marking on the timber scale coincide with the marking on the main scale. So we have the 4 here, and also there's one line at the bottom which represent 4.5. So for this case, our reading will be 4.5 plus 12 here means 12 like this. After that, we add together, it becomes 4.62 mm. Now, let's learn how to check for zero error for micrometer screw gauge. Again, similar with the vernier calipers, we need to close the micrometer screw gauge completely and look at the scale. You get either no zero error, positive zero error, or negative zero error. So this is how it looks like when there is no zero error. The zero mark on the main scale is at the edge of the timber. The zero mark on the timber scale coincides with the datum line. So the correct reading will be just same as the measured reading. So like for our case, for example, it is 4.62 mm. B, positive zero error. So this will how it looks like when there is a positive zero error. The zero mark on the main scale is seen. And we check which marking on the timber scale coincides with datum line. So for this case, the third marking. Hence, our correct reading will be measured reading minus zero error. For this case, 4.62 minus 0.03, which gives us 4.59 mm. Next, negative zero error. and this is how it looks like. The 0 mark of main scale is covered by timber. And check with which marking on timber scale coincides with the datum line. Count from 50 mark on the timber scale. Hence, for this case, 1, 2, and 3. So the third marking from 50 mark. Therefore, the correct reading will be measured reading minus 0 error. For this case, 4.62 minus negative 0.03, which should give us 4.65 mm. Measurement of time. The SI unit for time is seconds, symbol S. In physics lab, we use analog or digital stopwatch to measure time. So this is analog stopwatch. The first button is the start or stop button, and the second button is the reset button. We also can observe that there's a long needle, which is the second hand, and the short needle, which is the minute hand. So the reading for this stopwatch is 44 minutes and 18.2 seconds. This is a digital stopwatch. Okay, so the button is very obvious, right? We have the reset button at the left and we have the start and stop button at the right. And to take the reading is very straightforward. Just read from the digits shown on the screen. So for this case, the time is 8 minutes 55.05 seconds. Now, let's talk about a very popular experiment related to measurement of time, which is to find the period of a simple pendulum. This diagram shows the setup of the experiment, where we'll hang a box with a thread. Then we use a ruler to measure the length of the pendulum, and we use the stopwatch to measure the time. So one complete oscillation will be from A to B, then from B to C, C to B, and B back to A. So stopwatch is used to measure the time taken for 20 complete oscillation, T20. The period of the simple pendulum, T, is calculated from the average of the time of 20 complete oscillation. So for this case, T will be T20 divided by 20. Why we take 20 complete oscillations, not 1? The reason is to reduce human error because there is human response time to start and stop the stopwatch. Why the angle of oscillation, the theta, is less than 10 degrees, right? To prevent the conical oscillation of the pendulum. Furthermore, angle of oscillation does not affect the period. So what is conical pendulum? This diagram shows the conical pendulum, which is undesirable when conducting this experiment. So the formula to calculate the period of a pendulum is T equals to 2 pi square root of L over G. The period of simple pendulum is independent of the angle of oscillation theta, the mass of the box m. But the period of the simple pendulum is dependent on the length of the pendulum L and the acceleration due to the gravity G. Now let's look at the example. The bob of the pendulum is released at point A. Time taken for the pendulum to swing 20 oscillation is 8 seconds. Now calculate the period of the pendulum and what is the time taken for the pendulum to swing from A to C, then to B. So the solution is the period of the pendulum is T20 divided by 20. For this case, is 8 seconds over 20 and we get 0.4 seconds. If the time taken for pendulum to swing from A to C then to P is actually 3/4 of one complete oscillation. Hence, it will be 3 over 4 times the period of the pendulum. For this case, is 3 over 4 times 0.4, which is 0.3 seconds.
That's all for this video. Thanks for watching. Do you have any question or doubts to ask? Feel free to write down in the comments. I would love to hear from you. Do you like this video? Please don't forget to like it and share it. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form. Take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses. And most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.